Welcome to the Explainer. So, did you know the entire mathematical field of probability was essentially born just because a couple of 17th century French mathematicians wanted to settle a gambling dispute? It is literally true. Today, we're going to jump straight into the foundations of probabilistic theory to decode the precise math behind how chance actually works. Let's get right into it.
It all starts with one incredible, almost philosophical question, right? How do we calculate the unknown? It sounds like a totally impossible task, but predicting the likelihood of an event really just comes down to three fundamental mathematical formulas. And by the end of this explainer, you'll see exactly how these three equations form the absolute bedrock for navigating uncertainty. Section 1. The basics of chance, building the foundation of probability. Okay, let's dive into this. At its core, probability is just a super simple ratio. It's your favorable outcomes divided by your total outcomes. So, say you want to roll a 6 on a standard die. Your favorable outcome is just that one specific side. The total outcomes, well, that's all 6 sides. So, your probability is simply 1 divided by 6. Easy, right? And this brilliantly illustrates that concept. Think of all possible outcomes as, say, an entire donut. Your favorable outcomes, the specific event you're actually looking for, represent just one delicious slice out of that whole pastry. And naturally, the larger your slice of favorable outcomes, the higher the probability of that event actually happening. Let's really cement this equation in our minds before we add any extra layers of complexity. Probability equals favorable outcomes divided by total outcomes. Honestly, whether you're pulling a winning ticket out of a giant chest or, forecasting the weather, keep this exact ratio firmly in your mental toolkit. It's the building block for the whole shebang. Section 2. When conditions apply. Introducing conditional probability. Because you have to ask, what happens to our math when our probability is constrained by a previous event? Well, here is our second fundamental formula, conditional probability. P of A given B equals the intersection of A and B divided by P of B. Now look, I know at first glance that mathematical notation looks a bit intimidating, but please don't let it fool you. This is really just a clever variation of the exact same basic foundation we just laid down. Let's break this down step by step so we don't get overwhelmed. Imagine, for instance, drawing a card from a standard deck. Step 1, we look at the probability of event B. That's our P of B. Step 2, we find the intersection where both event A and event B happen together. And finally, step 3, we divide that intersection by the probability of B. Let's look a bit closer at that denominator, P of B. Because we're dealing with a conditional probability, where we already know event B has definitely happened, P of B basically acts as our brand new baseline for total outcomes. So if you know the card you drew is definitely a heart, well, that's event B, and your universe of possibilities literally just shrank from 52 cards down to only the 13 hearts. And then up top, in the numerator, we have the intersection. This represents the highly specific scenario where both events overlap. Since our universe is already restricted to the world where you drew a heart, we're simply finding the slice of that restricted world where event A also happens. So if event A is drawing a queen, we only care about the queen that intersects with the hearts, you see? It is still just favorable divided by total, just inside a newly restricted universe. Section 3. Totally independent events, the disconnect in probability. So the crucial point is really this stark contrast. On one side, we have conditional probability, where an event completely changes the mathematical landscape. But on the exact opposite side, we have independent events. Think of them like severed links in a chain, where the events have absolutely zero mathematical impact on one another, a complete disconnect. For independent events, like rolling a die and flipping a coin at the exact same time, calculating the intersection is completely different. P of A intersect B is simply P of A multiplied by P of B. Let's walk through this calculation together, and honestly, I have to say it is so wonderfully straightforward compared to those conditional constraints. First, you just find the probability of event A. Next, you find the probability of event B, and finally, you literally just multiply P of A by P of B. Because they don't influence each other's outcomes at all, their combined probability is just their individual probabilities multiplied together. Now, what's really interesting about this slide is the sheer elegance of it. Independent events. P of A intersect B equals P of A times P of B. No changing denominators to worry about, no shrinking universes of total outcomes. Actually, scratch that. It's just pure, totally independent multiplication. It's fantastic. Section 4.
The final calculation, applying the formulas. Let's move to and see how this builds into one cohesive picture. We have three precise mathematical scaffolding blocks, right? Basic probability, which is just favorable outcomes over total outcomes. Conditional probability, which is the intersection divided by the probability of the condition. And independent events, the simple multiplication of both probabilities. And, these aren't just dry equations trapped in some textbook. They're the literal rules that govern likelihood and chance in the real world. Every risk, every gamble, every single prediction relies on this exact math. So I'm going to leave you with this final thought. How will you use these exact formulas to calculate the probabilities in your own life?